Now, in a lot of these electrical loads, when you have a load here, could be, again, industrial load, could be as simple as something in your home. Most of these loads have a power factor that's lagging. It's extremely rare to find a load that has a power factor that's leading. Usually it's lagging, which means your load has a combination. So if it's a lagging power factor, your load is going to be a combination of a resistor and what? An inductor. And the only way, if you remember from math, the way we calculate the power factor is equal to cosine theta v minus theta I. So if you're looking at a complex number and you have a power factor, for example, of 0.8, then you know what that angle. If you have a lagging power factor, that means your angle is positive, and that's what you're looking at. This is theta. This will be a lagging power factor. You have that imaginary piece, that's the Q here, that's the imaginary, and this is the real. We use R, what did we use last time? R plus P plus JQ, right, for complex power? I forgot what we used for letters. So if you want to improve the power factor, what you want to do is basically shrink that theta. How do you, if you shrink that theta to a smaller value, let's say you go from 30 degrees to 10 degrees. If you can shrink that theta, that becomes the new theta. Now you'll have a higher power factor. And if you look at that picture, you'll notice that P, which is the average power, is not changing. But all I'm doing is what? Reducing that Q, that imaginary portion, the reactive. Well, how do you reduce that? The only way to reduce it is you need a negative J to cancel some of the J's here. And negative J, the only way to get a negative J is by putting a capacitor in parallel with that load. That will bring actually that power factor, that angle down to a smaller value, and you will see improve the power factor by whatever number you improve it by. I'll do an example in a few minutes. But that's really what I'm looking for. I need to add some negative J there in the problem to bring this one down.
You want to put it in parallel?
Well, it has, you'll see that, yes. It will be in parallel. And the reason it's in parallel there, I'll give you the reason why. Because if I have this load here, and I put a capacitor in parallel with that, we'll call it ZC, right? And I put a voltage here, and there's my current I. Well, if you look at this, we'll call this current, this is I sub L. We'll call this current I sub C. So now, the complex power for the entire system here, complex power is what? S equals V times I conjugate. But if you look at I, what is I equal to? Isn't that I sub L plus I sub C? So you can say the complex power is V times I sub L plus I sub C conjugate. And if you multiply that through, you'll have V times I sub L conjugate plus what? V times I sub C conjugate. So what does that mean? This is S for the load, or right? and this is the complex power for the capacitor. And when we do the capacitor, you will see this will not have any real portions, only imaginary value. The impedance of the capacitor is negative J. The current and the voltage in the capacitor are going to be off by negative 90 degrees. So this will be purely reactive. It will not have any real portion. So this will be like negative 50 J watts there. This will be 200 watts plus J 50, you know? So when you add them together, that negative J will lower that value. So that's why you want to be in parallel there.
Okay.
So let me give you an example with numbers in it. But that's the reason why we're doing this, so you can add them. Let's say I have electrical load, and I'll put some numbers in it. Here's my load, and it has 50 kilowatts. It has a 0.8 power factor, and it's lagging. So that's my load. Right across that, we have a voltage source here. We'll say 230 volts RMS. And as you know, 0.8 power factor is not bad, but I really like to change it. I like to make it better. So what I'm going to do here, I need to add something here, and I'm not sure what to put there. I just mentioned it should be a capacitor, but let's say I don't know what that is. Let me add something here, some impedance, and we'll let the math take us and tell us if that's an inductor or capacitor. What is it? I want to attach something to this such that now the new power factor for the whole thing, the new power factor to go from 0.8, let's do 0.95. So what should we put there? I said, oh, it has to be a capacitor. Let's see if the math would say it has to be a capacitor or not. Let's look at the load here. So I don't know what should we call this. Should we give it a different name? I'm not going to call it load. Any idea what should we call it?
The middle thing.
This guy. Or call this one load 1, that's load 2 maybe? This is load 1, this is load 2. So let's look at load 1. Let's find S for load 1. What is that equal to? We know it has a real portion, it has imaginary portion Q. So if I draw a picture of load 1 here, we know the power factor is what? It is lagging, that means the angle is positive. This is your S1 for load 1. I know the real portion of it, P1, Q1. I know what P1 for that, which is what? 50,000, 50 kilo. The units are watts, that tells you that's average power. That's why the unit's so important there. I also know what that angle is. What is that angle?
Inverse cosine.
Yes, the inverse cosine of 0.8, which will be what? Where's my calculator there? Clear, F18. Inverse cosine, second cosine, where's cosine? Third cosine, green cosine of 0.8. Roughly 37 degrees, 36.8699, right? Can you find what Q1 is now?
Yeah.
Yeah, just trig. We can say tangent 37 degrees is equal to Q1 over 50K or 50,000. What's Q1 equal to? Tangent of 37 times what? 50,000. Roughly what? 37.5. If you carry all the numbers from the previous one, instead of just 37 degrees, if you use 36.8699, let's see, what is the exact number? Tangent. Let me get that angle. Times 50,000. 37,500 on the money, if you carry all the digits. So I know what S1 is equal to. That's the complex power for the combined, for load 1. Not the combined, for load 1, this guy is going to be what? 50,000 plus J 37,500. Now let's look at the combined load. That's the whole thing. Forgot to look, see if I'm recording actually. The combined load, that's the whole thing. S total here. What is it? It's going to have the P total here plus JQ total here. Well, we're saying what we need to do, raise the power factor. I'm not changing the 50 kilowatts. So what I'm looking at now I don't want to change that because that means I got to pay for more electricity if I raise that one. I don't want to. So I want my problem to look like this now. I still have the 50,000 here. I need to know what Q is, but I know what that angle is. This is the inverse cosine of what? 0.95. So let's see what that number is. Inverse cosine 0.95. Roughly 18 degrees, right? So now we go tangent 18 degrees equals Q over 50,000. So tangent, let's pick that angle, times 50,000. 16,434. 16,000. If you want to use significant digits, well, I'll go 16,434. That's fine. So what's S total now? It's the 50,000 plus J 16,434. Notice what we did. By putting that device there to reduce the power factor, we shrunk that imaginary portion. It used to be 50,000 plus J 37,000, now 16,000. That's what my goal is.
We want our new one to be that?
Yeah, you want that J value to be 0, ideally.
Yeah.
If J is 0, you're getting 100% power factor. Your power factor is 1. You're getting every single thing that's being shipped to you. You're not losing anything. That's not going to happen in real life. So you want the power factor to be 0.9, 0.95, 0.97, which means the closer to 100%, the smaller that number is. So now, S total here, we just wrote that early, equals S for load 1 plus S for load 2. So 50,000 plus J 16,434 equals load 1 50,000 plus J what? 37,500 plus S load 2. And you can see the math that 50,000 cancels the 50,000s on both sides of the equation. So S for load 2 is going to be what? This minus that. So 16,434 minus 37,500. It's negative 21,066 J. Well, the fact this is negative, notice we're talking about complex power that's negative. I don't have my notes, I threw them in the trash. I said before, because after the class I throw them. When I start talking about complex power, I said if your load is purely reactive, I did it purely resistive, purely reactive, one of those alternative ones. I can look on the website because I posted the notes. If J is negative, if this one is negative, that tells you have what? Capacitor. If J is positive, you have what? An inductor. I think I wrote that somewhere in the notes. So that tells me really my load is a capacitive load. I have a capacitor. And the next question is, what is the value of that capacitor now? Can we get what the value of the capacitor might be? So now we established that load 2 is a capacitor. And here's what I know about load 2. That's load number 2. We established it's a capacitor. What is the value of that? How many farad? What else do I know about that? I know the voltage cross, that one is what? We did that. Where was it? 230 angle 0. Where is it? Right here. 230 angle 0 RMS. Just one little correction here. Usually most books, where the arrow is, that's where the plus is. So you don't want to put arrows on both sides. Plus means that's the arrow is a plus. I also know the current through that, or I can find the current through that.
You would just solve directly for Z?
Well, we're going to solve for Z now. So how do we figure out what Z is? We know the voltage. If I know what this current is, then Z here, whatever Z here, Z will be what? Ohm's law, it's 230 volts, RMS, divided by I sub 2, Ohm's law. So you want to find what I sub 2 and RMS here. So how do we find what I sub 2 is? Well, I know what the, I've also forgot to write the complex power here. For that is what? Negative 21,066 J, right? What's the definition of complex power? V times I conjugate. I know this is what? Negative 21066 J. I know that's 230 times I2 conjugate. Can I solve for I2 conjugate? Just divide that number by 230, right? And I came up with negative 91.6 J. So what is I sub 2? Positive 91.6 J. Once I have that, can I find what Z is? 230 divided by what? 91.6 J. 230 divided by equals, I came up with negative 2.51. Negative. And it should be a J with it, right? That's what Z is. We said that's a capacitor. We already established that. Well, what's the impedance of a capacitor?
1 over J omega C.
Yes, or negative J over omega C, either way. So the negative 2.51 J equals 1 over J omega C, or you can take the J to the top, make it negative J over omega C. Let's assume we were using an outlet in the USA. If you're using an outlet in the USA, what's your frequency? 60 hertz. So what's W? 2 pi F. 2 times pi, which is, leave it pi, F is 60, you end up with what? 377. The negative J cancels the negative J, you end up with 2.51 equals 1 over 377C. The J's will cancel each other out with the minus sign. 377C equals 1 over 2.51. C equals what? 1 over 2.51. Divide that by 377. So 2.51 times 377 equals 1 over that. And I came up with 0.001057 farad. We usually don't like to write a capacitor like this. So if you want, you can make that 1057 microfarad or 1.057 what? Millifarad. So roughly 1,000 microfarad capacitor. You put 1,000 microfarad, that will improve your power factor to a power factor of 0.9.
Is that what you said they brought in a capacitor
Yep,
the size
yep,
of the door?
yep. Because that thing, you know, first, keep in mind we're dealing with industrial. You can't just put like the ones you see in the lab, we put 5 volts across them. You put 15 volts, that thing will evaporate. You know, they can't handle that. There's a rating on them. Maximum watts on this one is this much, you know. So you got to use industrial type, and they're not small, you know. To put 230 volts across the ones we have in the lab, good luck. Take your oven, attach a little capacitor in the back, and make sure you have 230 volts going through it. You're looking to be melted, you know. But that's how we do power factor correction. It bugs me on the last video, I added wrong at the end. When I was doing the last step, I added the numbers wrong, and I wish I don't have the technology, I don't have the right software to go and fix it, so it's up there with a little error in it there, but I can't touch it. So I'll do more complex powers here. I'll make me one more example. And this just happened to be in your book as, I think, one of the drill problems. I'm going to assign some homework today. So let's look at that one. So this is an example, nothing to do with power factor correction, just one example, that's plenty. But example on complex power. I thought I heard some little kid. We have a voltage source of 120 angle 0 volts RMS. There's 1 ohm here. J10, 5, and we have a capacitor. And that's negative 10J.
That wasn't VRMS, we would just divide by square root of 2, right?
It becomes 1/2 complex. Yes, if you want to change, if you want to just change
If
that
we
one.
Say that wasn't VRMS.
Yep, if you want to switch that to RMS, you're right. If it's, you divide by the square root of 2, because sine, cosine, you know. But if you want to use complex power, instead of VRMS I conjugate, you can do 1/2 Vmax I max conjugate. Yeah. All right. Yeah, VI conjugate. So now, the question here, find the complex power. The book actually, our book gives you one example on complex power. That's this example, and that was it. So what we did last time was in your book. Absorbed by, the first question, the 1 ohm resistor. And I probably will not answer them in that order. 2, by the negative 10J capacitor. 3, by the source. And 4, by the 5 plus 10J impedance. So how much complex power here, 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 and here? Now we know the source has to do what? Supply. So that should be a negative. That's one of the questions I got on one of the videos. Can you explain what a negative power means? A negative, when you have a negative sign in the front, it means supplying the power. I need just to hire somebody to respond to these emails. Actually, that'll be cool. Because I never respond to any of them. I feel bad. I just don't have the time for it. What I could do right here, I could do what I learned in the first chapter in circuits 2, and that is combine these guys into one if you want to. Right? One impedance. I can combine them. If I do that, I can find that current. I can tell you how much complex power absorbed by this, how much was supplied by that. Is it Donna talking to that baby? Now I'm going to find the equivalent of these. What do we have? We have this one in parallel with that. So we have 5 plus 10J. These are connected in series. In parallel, that's what that line means, parallel, the negative 10J. And how do you find the equivalent value? Product over the sum. When you only have 2 of them, that's the quickest way. You multiply these 2. And when you add them, what will happen to the 10J and negative 10J? Comes a 5. Oh, it's been a while since I used this calculator with complex. I forgot. Is there a comma I have to put? Oh, no. So here we go. Times 5 plus 10J. I got what? Tell me if you got the same number. 22.36 angle negative 26.56.
Did you divide by 5?
Yep. what I did actually to cheat there, what's negative 10 divided by 5?
Just did negative.
Negative 2j times that. So instead of writing divide by, I just did it that way. And if we change that to rectangular, that will be what?
20 minus 10.
20 minus 10j, yes.
Can we just distribute that out like normal?
You could,
Yeah.
Yep.
Okay. I was-
because that would be what? If you remember, that's negative 2 times 10, that's 20, j squared is minus 1, so it's 20 minus 10j. Now, I can actually find the voltage here, and I can find the current there. Because if I know the voltage and the current, I'm almost done with the problem. What is the voltage here? We'll call it VL. What's the current here? We'll call it I. First, the current is an easy one to find. Ohm's law. 120 angle 0 divided by the sum of the two impedances. What's the sum here? 21 minus 10j. Right, come back here. 120 divided by 21 minus 10j. I got 5.16 angle 25.5, which if you simplify, that's 4.66 plus 2.2j. Right now I can tell you the average power, the complex power absorbed by the 1 ohm resistor and the source from that value. Right? So let me answer that. As for the source, complex power, we have a current entering the minus. That's a minus. Minus indicates, again, that's supplying power. It's V times I conjugate. So it's a negative. V is what? 120 times I conjugate. This is the I. What's the conjugate of that? 4.66 minus 2.2j. Negative 120 times 4.66 looks like negative 599, right? That would be a plus. Negative times a negative, that's a plus. 120 times 2.2, 264J. And what are the units for complex power? VA. Got the pen here. Where'd you go, pen? Hey, come back here. Now let's look at the 1 ohm resistor. High-tech room, huh? Let's look at the 1 ohm resistor. So what is the complex power absorbed by the 1 ohm resistor? Again, it's V times I conjugate. Well, I don't know what V is. I didn't calculate V for this, but I can use Ohm's law. V equals what? I times R. Isn't it? So that's I, R is 1 times 1 times I conjugate. So what is I here? 4.66 plus 2.2J times I conjugate 4.66 minus 2.2J. And what do we have for an answer for that one? If you do the math, the imaginary portion should be what? 0. So that's what? 26.6 plus J0. So if they ask for complex power, remember complex have real portion, the average power has imaginary portion, that's the reactive power. So if they want both of them, that's the value, that's the average power, reactive power is 0. There's nothing. And again, it's VA.
What is V? Volt amp?
Volts amp, yep. Now, these two here, I got a little problem. I don't know the voltage or the current through them. If I know the voltage, I can find the current through them, right? If somebody comes and whispers in my ear, say, the voltage is 17, oh, that's easy then. I know what that current is. And I know what this current is, if I know the voltage cross. Since these two are equivalent to this, I can find that voltage VL. Voltage division. Going back to circuits 1. So let me find VL here.
Let's do current division.
Or, actually, I don't have to voltage. I can do the current times that one, right? First to get that voltage. You know what the current going through that. We found what I is, and we know what the impedance. So maybe I'll do that instead of voltage division. I'll go VL equals, then we'll do current division after that to find the other current. Yes. I times 20 minus 10J. So I'll put it like this. To find this voltage, I'm taking the current going through it multiplied by that impedance. We know what that current. I just did that. What was it? 4 point something. It was 4.66.
4.66 plus 2.2J.
4.66 plus 2.2J times 20 minus 10J. You can put your calculator, actually, if you want it in rectangular mode, multiply them out. And if you do that, you end up with what? 115.2, you said?
Yes.
Minus what? 2.6J. Anyone else got that number?
Yep.
Okay. So now we know what VL is. You can do current division if you wanted to find that, or you can just divide them. You know what I sub 1, I sub 2, Ohm's law. V over this, that's I sub 1. V over that, that's I sub 2. So if you want to find I sub 1, it's V, which is what? 115.2 minus 2.6J divided by 5 plus 10J. And I sub 2 will be what? V, which is 115.2 minus 2.6J divided by what? Negative 10J. So do we have answers for them? Let me know if you get I sub 1, I sub 2. Mode. Let me go to rectangular instead of polar and see if that will do it.
That's both of them if you want.
I'll take the rectangular for I sub 1.
4.4 minus 9.32J.
And I sub 2,
0.26.
0.26.
Negative 0.26, right?
I negative.
No, because that's negative j on the bottom becomes a j on the top.
Plus 11.52 J.
11.52 j. Okay. Yeah, that makes sense here, because that negative j in the bottom, when you bring it to, becomes a j here over 10. So this will be a positive j, and this will be a negative j squared, which is negative 1. That'll make it a plus. So it should be a plus and a plus there, yes. So now if I know that, I know the voltage there too. So looking at that circuit, here we go. Complex power by the 5 plus the 10j. It's V times I sub 1 conjugate. We know what V is. We just did the math on that one. Where'd you go, V? Oh, right there on the top. I'm just blind. Right here. It's 115.2 minus 2.6j. I sub 1. This is I sub 1. I need its conjugate. What's its conjugate? 4.4 plus 9.32j. And do we have an answer? Let's see. 115.2 minus 2.6j times 4.4 plus 9.32j. I got 531. Let me know if that's what you got. 531, 530, whatever, plus 1062.2j. Is that what you got? VA. And now we can find the last one, the complex power absorbed by that one, which is V. Again, the V is 115.2 minus 2.6j times what? I2 conjugate. I2 conjugate will be 0.26 minus 11.52j. So 115.2 minus 2.6j times 0.26 minus 11.52j. Where's the j?
It's 1327, or negative 1327.
Oh, 28, right? Negative 1328j roughly. And now we answer all the questions on it. Complex power absorbed by the negative 10j, by that one, by the source. Source is supplying, the rest of them are adding. Now if we take these numbers and add them, do they add up to a 0? Curiosity. Let's take the sum of these 4 numbers. When I say 4 numbers, that's this. This, and the last 2 we just did this and this. Let's add the 4 of them and see what the result is. Negative 5. I gotta, since that's complex, has to go in parentheses. F1, 8, clear everything. Here we go. Negative 599 plus 264j. That's the first one. Plus the next one. Plus what? 26.6. That's it. Plus the next one, parentheses, 531 plus 1062.2. plus parentheses negative 1328J. Negative. Did you get, what'd you get for answers?
Negative 41.55 minus 0.2J.
Negative 0.2J. The 0.2 is the rounding error. 1328.
It'd just be 0, right? If you add
Supply absorbed there should equal. Yeah. Just add the three complex powers here. $26, add to it this, add to it that.
Again, negative 109 plus 1334 J.
I deleted mine, I don't know what I got in mine, you know. Hopefully, I didn't divide anything wrong, but I think my numbers are good there, you know.
It should be 0.0J.
Well,
That's what we should get.
unless, what is the problem? I forgot what the problem looked like.